5.2 Systems of Equations with Matrices. The definition of a matrix. An m by n matrix is a rectangular array of numbers with m rows and n columns. We say that the matrix has dimension m by n. The numbers aij are the entries of the matrix. The subscript on the entry aij indicates that it is in the ith row and the jth column. We can rewrite this linear system as an augmented matrix by writing the coefficients and constants with no variables. Elementary row operations. You can add a multiple of one row to another, you can multiply a row by a non-zero constant, and you can interchange two rows. So let's solve by matrix elementary row operations. First, rewrite this system of equations as an augmented matrix. Our goal is to get it into triangular form. The first coefficient of the first equation is already 1, so we will use the first row to change the 1 and 3 in the second and third rows into zeros. Multiply row 1 by -1 and add it to row 2. Multiply row 1 by -3 and add it to row 3. My goal now is to get a 1 in place of where this 3 is. Usually I would divide everything in this row by 3, but that will give me some fractions, which I would like to avoid if possible. I do notice that row 3 is completely divisible by 2, so if I exchanged rows 2 and 3, then I could divide row 2 by 2 and get a 1 in this spot. After exchanging rows 2 and 3, multiply the new row 2 by 1/2. Now the entry in the second row and second column is a 1, and we will use row 2 to change this 3 into a 0, getting it into triangular form. Multiply row 2 by -3 and add it to row 3. Now that your matrix is in triangular form, rewrite it as a system of equations. Use back substitution to solve for y and x. And your solution is 2, 7, 3. Row echelon form and reduced row echelon form of a matrix. A matrix is in row echelon form if it satisfies the following conditions. The first non-zero number in each row, reading from left to right, is 1. This is called the leading entry. The leading entry in each row is to the right of the leading entry in the row immediately above it. And all rows consisting entirely of zeros are at the bottom of the matrix. A matrix is in reduced row echelon form if it is in row echelon form and also satisfies the following condition. Every number above and below each leading entry is a 0. Here are some examples. The first is in reduced row echelon form. Leading ones have zeros above and below them, and shift to the right in successive rows. The second is in row echelon form. Leading ones shift to the right in successive rows and have zeros below them. The third is not in row echelon form, because the leading ones do not shift to the right in successive rows. Solving a system using Gaussian elimination means changing it to row echelon form, just like we did in example 1. Solving a system using Gauss-Jordan elimination means to change the matrix into reduced row echelon form. This will require you to obtain zeros above each leading entry in addition to below each leading entry. For number 2, solve by Gaussian elimination. First, write as an augmented matrix. Our very first entry in the first row and first column must be a 1, and fortunately this first row is divisible by 4, so I'll multiply row 1 by 1/4. Now we have our leading 1 in row 1. Use that to change the 3 and -2 into zeros. We'll multiply row 1 by -3 and add it to row 2, and multiply row 1 by 2 and add it to row 3. Now the entry in the second row, second column needs to be a 1. Unfortunately, this equation is divisible by 2, so I'll multiply row 2 by 1/2. But I also noticed that row 3 is all divisible by 5, so I'm going to multiply row 3 by 1/5 just to get smaller numbers. Now I can simply multiply row 2 by -1 and add it to row 3. The last step is to get the entry in the third row and third column to be a leading 1. Multiply the third row by -1/2. Now rewrite this as a system of equations and use back substitution to solve for y and x. Your solution is -3, 1, -2. Number 3 is asking us to solve by Gauss-Jordan elimination. But if you notice, this is actually the same system of equations we were asked to solve in number 2 by Gaussian elimination. In our previous example, we wrote the matrix in row echelon form, but for Gauss-Jordan elimination, we now need to write this matrix in reduced row echelon form. Rewrite the row echelon form you got from example 2. The way we turn entries into zeros is by using the row with the leading 1. So to turn this 2 into a 0, we're going to use row 2 and create a new row 1. The second and third rows remain the same. -2 times row 2 plus row 1 will give you a 0 as your entry in the first row, second column. Now it's time to turn the numbers above the third leading 1 into zeros. Because the leading 1 is in row 3, we'll use row 3 to eliminate -9 and 4. Multiply row 3 by 9 and add it to row 1. Multiply row 3 by -4 and add it to row 2. Rewrite this as a system of equations. See how conveniently reduced row echelon form gives you your answers. And you have the same answer, -3, 1, -2. Number 4, solve by Gaussian elimination. First, rewrite the system of equations as an augmented matrix. Rewrite this matrix in row echelon form. Then press play to check your answer. We already have a leading 1 in the first row, so we'll use that to eliminate the 2 and 1 below it. Conveniently, that also gives us a leading 1 in row 2, so we'll use that to eliminate the 1 in row 3 below it. Uh-oh, if we rewrote this as a system of equations, it would say 0 equals 18. That's not true. So this is an inconsistent system, and there is no solution. Number 5, solve by Gaussian elimination. Rewrite as an augmented matrix, and then use row operations to write your augmented matrix in row echelon form. We do not have a leading 1 in our first row, but we have a 1 as the first entry in our third row, so why don't we just exchange rows 1 and 3? Now use the leading 1 in row 1 to eliminate the -1 and -3 below it. Conveniently, row 2 already has a leading 1 now, so we'll use that leading 1 to eliminate the -2 below it. This is giving us 0 equals 0. Rewrite it as a system of equations. It is not enough to simply write that this has infinitely many solutions. You must write the solution as a point made up of parametric expressions, representing the parametric equations for x, y, and z. Solve for y in equation 2, and then solve for x in equation 1. Use t as your perimeter and let z equals t. That makes this a dependent system with infinitely many solutions in the form 7t minus 5, 3t plus 1, t. That means if you chose any value of t and plugged it into these expressions, you would get a point that is a solution to this system of equations.